On exponential Diophantine equation 2x plus 41y equals z2. Abstract. In this paper, we used different method and find all solutions of exponential Diophantine equations 2x plus 41y equals z2 where x, y, z are non-negative integers. Keywords and phrases. Exponential Diophantine equations 2010 Mathematics Subject Classification 11D09, 11D99. 1. Introduction. Diophantine analysis deals with various techniques of solving Diophantine equations. If a Diophantine equation has variables as exponents, it is said to be exponential Diophantine equation. In this note, we will find all solutions of exponential Diophantine equation 2x plus 41y equals z2 where x, y, z are non-negative integers. 2. Main results. Theorem 1. 4. The only solutions to the Diophantine equation 8x plus 41y equals z2 in non-negative integers are given by x, y, z, 1, 0, 3, 1, 1, 7. Theorem 2. 1. The equation 2x plus by equals z2, bx, y, z. N. GCD, bz, equals 1b1 x1 y equals 3 has only solution, bx, y, z, equals 17, 7, 3, 71. Theorem 3. 5. The equation 2x plus by equals cz admits the solution 4. Theorem 4. The only solutions, x, y, z, n3 to the equation 2x plus 41y equals z2 are 3, 1, 7, 7, 1, 13. Prove. Let x, y, z n. First, we determine the parity of x, y, and z. Since x equals 1, then, obviously z is odd. Moreover, it's clear that the equation 2x plus 41y equals z2 may admit a solution, xy.z, n3 provided y is odd, otherwise, we will have a contradiction. 2. Suppose now that 2x plus 41y equals z2 holds true for some tuples, x, y, z, where x, y, and z are all odd. We consider two cases, case 1 where 3x and case 2 is where 3 is not divisible by x. Case 1. If x equals 3k, where k is natural, and 2 is not divisible by k, then we have 3k plus 41y equals z2 or equivalently 8k plus 41y equals z2. In view of Theorem 1, the only solution, kyz, xy.z, n3 is 1, 1, 7. Hence we get 3, 1, 7 as only solution to 2x plus 41y equals z2 in n, for x divisible by 3. Case 2. Now, suppose that 3 is not divisible by x. First, we suppose that x equals 1. Then we have 2 plus 41y equals z2. Note that 41y equals 1, mod 4. Hence we get 2 plus 41y equals 3, mod 4, while z2 equals 1, mod 4, a contradiction. Hence x.1. Apparently, 41 is not divisible by z because of congruence 2x equals 0, mod 4 1. So for y equals 3 the only solution we get is, xyz, equals 7, 3, 71, Theorem 2. Now consider the case for y equals 1. Since z has quadratic exponent, we know that the equation 2x plus 41y equals z2 may admit a solution in n such that x 50, 41, 41. Theorem 3. 13, 2. Since the bound for x is small, one can effectively use a simple mathematical program to find whether there is any integer x on the interval 1, 41, that makes the quantity v2 plus 41 an integer. Nevertheless, the values of x that could satisfy the equation may be obtained theoretically, and this we show as follows. Rewriting 2x plus 41y equals z2 as 3, 2x plus 5, slash 3, equals z plus 6, z6. We see that z must be at least 7. We know that z is odd, so z equals 2c plus 3 for c equals 2. It follows that 2x plus 41 equals 2c plus 3, 2 equals 4c2 plus 12c plus 9 or equivalently, 4c2 plus 12c2x equals 32. Suppose that c is even, say c equals 2sm for some sm.n where m is odd. Then, 2x, 22s plus 2xm2 plus 2s plus 2x3m1, equals 25, 1. Recall that x1, 3 is not divisible by x and x is odd, so x must be at least 7. Thus from 1, we get a contradiction. Hence c cannot be an even integer. Hence, c is odd. For x equals 7 and c is odd, we have 2x plus 41 equals 4c2 plus 12c plus 9. Hence 2x plus 32 equals 4c2 plus 12c, which gives 2x2 plus 8 equals c2 plus 3c. So 23, 2x5 plus 1, equals c plus 3. Now, c being odd gives c plus 3 equals 8 or c equals 5. So 2x5 equals 22 and so x equals 7. Finally this gives the solution, xyz, equals 7, 1, 13. Hence the final solution for xyz, n3 to 2x plus 41y equals z2r, 3, 1, 7. 7, 1, 13. Remark 1. Further, if x, y, z are non-negative, then in this equation, x and z can never be 0. Suppose if x equals 0, the equation becomes 41y equals z2. Minus 1 will lead to a contradiction. Indeed, for y and z in n, we have 41a, 41a minus 1, equals 41, 41a equals z plus 1, z1, equals 2 where a plus equals y. Evidently, a equals 0 gives 41 equals 3, which is impossible. If z equals 0, then 2x plus 41y equals 0, again impossible for non-zero x and y. If y equals 0, then equation becomes 2x plus 1 equals z2, which have a solution, 3, 0, 3, 3. 3. Conclusion. The all solutions of Diophantine equations 2x plus 41y equals z2 where x, y, z are non-negative integers is 3, 0, 3, 3, 1, 7, 7, 1, 13.